This lesson is going to talk about Faraday's law. So we've talked about Lenz's law. Lenz's law says that a change in magnetic flux will induce a current. And Faraday's law is going to allow us to take that idea and figure out what size current is induced. So Faraday's law officially says an EMF, or little epsilon, is induced in a conducting loop if the magnetic flux through the loop changes. If the flux is changed by delta phi during the time interval delta t, the EMF is, and this is the equation that we have on your AP Physics 2 equation sheet. It says the induced EMF, which is what we've also used in a battery as a change in potential. The induced EMF equals negative times the change in flux, magnetic flux, over the change in time. And the direction of the EMF is, or the direction of the current, is given by Lenz's law. You'll notice that there's a negative here. This negative is because the induced current will oppose the change in magnetic flux. So if the magnetic flux is going up, the induced current will go opposite of that. So let's do an example problem. This is the equation we have from our Physics 2 equation sheet. So this picture shows a 10 centimeter diameter loop in 3 different magnetic fields. The loop's resistance is 0.1 ohms. For each case, determine the induced EMF, then the induced current, and then the direction of the current. So this is basically 3 different problems. We're going to start with A. So for A, we have a magnetic field. It's increasing at 0.50 Teslas per second. The equations we're going to use are the equation for the induced EMF and the equation for flux from Lenz's law. So first we need to find the induced EMF. Our induced EMF is negative delta phi over delta t. And in this case, our angle, you can see it is perpendicular to the magnetic field, so our angle theta is going to be 90 degrees. Our EMF equals the delta phi over delta t, and remember phi is b cosine theta times a. We're going to rearrange this a little bit to put the b on the right hand side. So it's going to be a times cosine of theta times delta b all over delta t. And the reason is because the delta b over delta t is given to us. This is the change in magnetic field per unit time. We're going to plug our values in. We know the area of our circle is going to be pi r squared. It's a 10 centimeter loop, so that means its radius is 10 centimeter diameter, so its radius is 5 centimeters. So pi r squared. We have pi, the radius, squared, times the change in magnetic field per unit time, and all of that times negative. That gives us an induced EMF of negative 4 times 10 to the negative third volts, which is negative 4 millivolts. That's going to be the EMF that's induced in this wire. Now that we have the induced EMF, we can find the induced current by using Ohm's law. Basically, the voltage divided by the resistance equals the current. We're given the resistance of 0.1 ohms, so we take our induced EMF divided by the resistance, and we get a current of negative 40 milliamps. The negative just telling us the direction is going to be opposing, creating a magnetic field to oppose this magnetic field. Finally, we want to know the direction of the current. Well, we could get it from the negative here. We can also use our right-hand rule to know that if we have an increasing magnetic field coming out of the page, we're going to use our Lenz's law. Increasing magnetic field going out of the page, our induced magnetic field is going to want to go into the page. Use your right-hand rule. Put your thumb around the direction of the current that your fingers would go into the page, and you will get a current that goes clockwise. So our induced current is clockwise. So that's the first part of problem 1. For the second part, now we have a decreasing current of 0.5 Tesla per second. This is pretty similar to the first problem. Our setup is going to be the same. We're still going to be at a 90-degree angle. And our equation is the same. The difference is that our delta B over delta T is a negative instead of a positive. So now we have a negative 0.5 Tesla per second. Everything else is the same in here. Our area is the same. Our equation is the same. We end up with an induced EMF of 4 millivolts. And we can use that with the resistance to get our induced current. Our induced current is going to be the induced EMF divided by the resistance, and that gives us 40 milliamps. Now, for the direction of the current, we have a decreasing magnetic field going into the paper. So if we have decreasing going in, we're going to want to resist that decrease. So our induced magnetic field, instead of going opposing a decreased magnetic field, is going to create a magnetic field that goes also into the paper. To create a magnetic field going into the paper, our current is going to go clockwise, because it's going to, if you put your thumb going clockwise, we have a magnetic field going into the paper that will oppose a decreasing magnetic field or magnetic flux. Finally, we have a loop that is perpendicular to the magnetic field. The magnetic field is decreasing at 0.5 Tesla per second. We use our same equation, but now our theta is 0 because our angle is rotated 0 degrees from the magnetic field. And that gives us a induced EMF of 0 volts. You can see that because there's actually no flux going through the loop in this case, because it is parallel to the magnetic field. That means that our induced current, if there's no voltage, our induced current must also be 0. And the direction of the current, since there's no change in flux, the induced current is also 0. So there is no direction to it. Finally, I wanted to talk about a particular example of an induced EMF that's a little bit more complicated. Instead of a simple loop, we could have a solenoid or a series of coils. If I have a series of coils, I'm going to have more flux, and as a result, I will have a greater EMF. And the equation is pretty simple. This equation is not on your equation sheet, but it is intuitive if you think about what it says. Now, previously we just said EMF is negative delta phi over delta t. Now we have EMF equals negative n times delta phi over delta t, and n is just the number of coils. So if I have one coil, then I have my equation from the equation sheet. But if I have 3 coils, I just multiply that voltage by 3. So as the number of coils increases, the induced EMF will increase also, and it's by a factor of the number of coils.